Hello everyone, welcome back. In this video, we are going to learn and practice the last but not least session of this training course. In my last video, we have learned that using the product approach can help us to generate the most realistic distributions of soil and carbon, and at the same time inspiring more process understanding on land carbon cycle. In this video, I will lead you to use the product approach to replicate part of my research. And in the future, you are encouraged to use this approach to your own study. In my last video, we went through the workflow of product. And in this practice session, I will help you to exercise the training, to exercise the neural networking part of the product approach. As we have discussed, the rationale of using neural networking in product is simple because all the parameters in process-based models are all representing ecological or biological processes in land carbon cycle. We want to take those parameters at each side as part of the properties of the soil and predict those parameters by environmental variables. As we can see from this diagram, on the one hand, we can collect local environmental variables such as temperature, precipitation, soil texture, and so on. On the other hand, we get optimized parameter values in the side-by-side data assimilation. Now we want to build connections between these two parts. But one problem is that the relationships are not necessarily to be linear or so-called explicit. To overcome this problem, we introduced the neural network. Basically, we take the local environmental variables as the input of the neural network, and based on the input, the neural network will give predictions on optimized parameter values. By certain algorithm in the neural network, we can train the neural network with the results from side-by-side data assimilation, so that the neural network can eventually give predictions on parameter values that are most close to the optimized parameter values in the side-by-side data assimilation. To better understand how the neural network works, let's first have a look at an example. When we are making decisions in our daily life, we are actually following similar algorithms in neural network. Our brain gets all the external information from the environment as the input, and when all the input then all the input will be in some way transported to the neurons for processing and generating different possibilities. When making decision by some algorithm, we put all those possibilities with different weights to indicate how likely the idea will be accepted as the final decision. After all this, we make the final decision. That is how our brain works in making decisions. And actually, the neural networking follows the same way with our brain. To generate the final decision, the neural network need to have inputs, to have the neurons and the neuron weights as the main structure of the neural network. In my research, the inputs are the environmental variables, which can be anything you can come up with to be relevant to parameters. The neurons are the basic unit of the neural network and generate all the possible predictions for the next layer or just as output. The neuron weights are the weights of the neuron values. By combining all the possible values with weights, we can get the neural network predictions. To make our decision or prediction more variable, actually in generating the weights of neurons, we can apply an activation function to generate more non-linearity. After all these are set, the neural network still need to be trained so that the neural network can know which neurons prediction is more reliable and should be put to more weights in the future. We therefore need a loss function in training the neural network. The loss function is very similar to the cost function in the MCMC algorithm, as mentioned in lecture 6.2. It will quantify how different the predicted parameter values are from the real parameter values. And of course, we use the results of side-by-side data simulation as the training target. After we get the loss function value, just as what we did in the MCMC algorithm, we still need an algorithm to determine how to adjust the model. In neural network, we have the optimizer to adjust the weights of neurons so that we can find the lowest loss to optimize neural network performance. So now we know that the basic settings of a neural network. We have to have the input, the output, the hidden layers, the neuron numbers at each layer to build the neural network, and the approach determines how many iterations you want the neural network to be optimized, and the batch size indicates how many data you want to use at one batch in optimization. At the same time, we can also change the hyperparameters to optimize the neural network. For example, you can determine your loss function, activation function, and the optimizer. Let's first have a try on a typical neural network used in my research. If you want to use your own computer to run the neural network, you can download the code package I shared with you and find the Python code via the directory in the gray box. The default setting of the neural network structure has been marked as red in this slide. If you want to use Carbotron to do the exercise, you may operate Carbotron and select the unit 10 and then select the exercise as task 1. You may need to choose a directory pathway to store the output, and here is an example directory. And then you may click the Run Exercise button to run the typical neural network task. If you want to look at the code, you can either open the code via the button of open source code, or you can check the code in the package I shared with you. After running the task 1, you can have the output figure reporting the losses in the training and the validation sites. Your figure may not as complete as I showed here if you are using Carbotron, because we want to save computation time. The default approach was set as 1200. If you want to have satisfactory results, you may need to set the approach as at least 2000, ideally 4000 or even more. At the same time, you can also get the figure to describe how well the predictions fit the side-by-side data simulation results. In task 1, after the neural network training, we use the predicted parameter values in the model to simulate uh, soil organic carbon content and compare the simulation with the observations. You can also check the output figure. If you want to use your own computer, you may need to operate the R language code in the gray box and check the results in the directory path as shown in the green box. Also, we have other output figure describes the predicted parameter maps. Later in task 3, we are going to use these maps to generate soil and carbon distribution across the US continent. Again, if you want to generate this map on your own computer, you may need to operate the R language code in the gray box. In using the neural network to predict parameter values at the beginning, the neural network results may not as good or even worse than conventional methods. We actually need to tune the neural network for better performance. I will briefly introduce some common procedures. First, if you find the predicted parameter values do not fit well with the real values, then you may need to consider to add more layers or more neurons in each layer of the neural network. At the same time, you can also consider different activation functions or optimizer options. Sometimes we may also encounter, the so-called overfitting problem, where in the loss figure, the loss of the validation site is much larger than the training site. When the loss of the training site continuously decrease, the loss of the validation site may increase. In this case, we can make early stopping to shorten the approach at a reasonable level so that the performance of neural network can be optimized. At the same time, we can apply the so-called regularization in the neural network. The regularization actually puts a penalty over the weights of neurons to avoid one neuron in the neural network has too much influence in the final results. This is more advanced setting, and we may not touch too much in the training course. If you are interested, you can refer to the website I listed here. Similar to regularization, if we do not want to one neuron in the neural network has too much information, too much influence in the final predictions, we can also use the drop out setting. In the dropout, we can randomly permute some certain percent of neurons in each approach of optimization, and therefore the performance of neural network can be more stable and robust. If you checked the default setting in task 1, you may find that actually we used the drop setting in the neural network. After learning some basic tuning tips in the neural network, let's do the second task. If you want to use your own computer, the three scripts used in task 2 are in the gray box. If you want to use Carbotron, you may follow the procedures on the screen. After setting basic structures of the neural network, you can also change the hyperparameters we mentioned in the previous slides. You can try different combinations of these options to train the neural network to see if we can get better performance. After running task 2, you can get the output figures as shown as in task 1. You can compare your results in your test with the default setting. In task 1 and 2, actually we exercised how to use a neural network to predict parameter values at individual sites. That is a core part of the product approach. When we have a multi-site data, actually we can also apply batch data simulation to optimize parameter values, but the final optimized parameters will be spatially homogeneous instead of spatially heterogeneous as shown in product approach. In the batch data simulation, we put all the observations at one time in the cost function in MCMC algorithm, and therefore get one set of posterior distributions. In theory, this method should harmonize all the information between the model and the data and optimize the model performance. Because the batch data simulation is time consuming, especially when there are tens of thousands of profiles. I just showed here the final results, and we will not exercise this part. But please keep in mind that after batch data simulation, there is only one set of posterior distributions that will be applied to the whole region in model simulation. To compare how the product differs from batch data simulation, here comes the task 3. You can select the optimized parameter results in task 1 or task 2 to the CM5 model and then generate a soil and carbon distribution map. Please be reminded that the batch data simulation results is given, and you may need to find the directory as I showed here in your Carbotron package. If you are using your own computer, you may run the code on the screen. Please note that you may need to set some variables in the code to generate results by different methods. Here is the code for generating figures and maps. In the output figures, we can first compare the agreement between model simulations and observations by different methods. We can clearly see that a product approach is much better than the results from one batch data simulation. Also, we can have the soil and carbon distribution map by different methods. So here comes the end of this training session. For saving computation time, we shorten the training approach, so you may not get as good as results as I showed here in the slides by the Carbotron. We highly recommend you to first use the Carbotron to get familiar with these 3 tasks, and then use your own computer to do the exercise again. If you have any questions, please feel free to ask me in the Slack or directly contact me by email. Thank you for watching, and let's explore the infinite possibilities with big data.